And our final speaker, after an awesome day, I would like to present Pedram Hassanzadeh, and he's an assistant professor at Rice University, and he's been doing lots of work, again, with the weather, climate, machine learning world. I feel like every few days you guys have a new paper coming out that I have to read. This is part of my motivation as I get it straight from the source here. So thank you, Pedram, for wrapping up a great day.
Okay, great. First of all, I'd like to thank the organizers for this great workshop, and also I'd like to thank the audience. I know it's probably late in the day for some of you. So today I'll tell you briefly about some of the work that we are doing on building physical constraints into neural networks for weather climate modeling. And specifically, I'm going to talk about our work on subgrid-scale modeling or closure modeling that the team and Pierre nicely talked about in the earlier presentations. And the test case that I'm going to use is two-dimensional turbulence. It's a rather simple, it's a toy model. It still shares some of the key characteristics of turbulence in the atmosphere and ocean. And I think it's still some of the work that I present here is going to be applicable to problems more broadly in weather and climate modeling, modeling of turbulent flows, and multi-scale nonlinear systems. The work that I'm presenting is mostly from a work that is led by Yifei Guan, who is a postdoc in our group at Rice. So we already had a lot of great presentations, so I'm going to very quickly go to my introductory slides. So as you know, simulating weather and climate system is complicated. One of the main reasons is that we are dealing with a multi-scale system. This cartoon here just reminds us of the broad range of length scales and time scales that we are dealing with and in the atmosphere alone. Even though in many problems, we are mainly interested in what's going on in the large and with the large and slow variables that collectively I'm going to show with variable X in the next few slides, we also cannot ignore what's going on at the smaller and faster scales, which I'm going to collectively show them with variable Y. Now, as you know, the traditional approach to deal with these kind of multi-scale systems has been to use a coarse-resolution numerical solver to solve the governing equations that are closed in the large scale variable X. We can solve this, for example, in climate modeling on the resolution of around 100 kilometers. But then we will need closure, as Tim already discussed. We need basically parameterization for subgrid scale processes, everything below the resolution of the numerical solver. And so basically, generically, I represent that with function P that we basically for the larger scales, for the resolver scales, we can basically calculate what the effect of the smaller scales are. And these are called parameterization. And there has been decades of work on physics-based parameterizations for various processes. There has been a lot of progress, but it's still clearly we need better ones to better do climate projections and predict extreme events. So in the past few years, there has been a lot of interest in what machine learning can do. One way that some studies have looked into what machine learning can do is to basically use machine learning to learn this relationship, to learn a closure between the resolver scales and basically the subgrid scales. You might use machine learning to estimate some of the key parameters in a current parameterization, or what I'm going to focus on is basically when we do what I call non-parametric data-driven parameterization, or DDP, where you don't assume anything about the structure, about the functional form of how X and Y relate to each other, but leave that to a neural network. So like many problems in applications of machine learning to weather climate modeling, once we figure out what is the specific application, let's say it's non-parametric DDP, there are still a lot of questions and challenges, and many of them actually opportunities that we have to address. We have to basically figure out what is the machine learning method to use, how to deal with the problem that we don't have high quality data in many of our problems. So we are in the small or poor data regime. How to incorporate physics or some of the properties of the equations that we know of into the neural network, how to deal with interpretability, generalization, which here specifically I'm talking about extrapolation, as already we heard about this from a number of talks. For example, if the forcing on the system increases, or if you think about the turbulent flow, if the Reynolds number increases, how to deal with this extrapolation problem. And at the end, we might build a good neural network that does well offline, but then when we couple it with the numerical solver, many studies have seen basically instabilities. So my group has been working on each of these items for the past few years. But today I'm first going to talk about this issue of instability, where we try to use some of the domain knowledge, basically in terms of backscattering analysis, which is looking at interscale energy and entropy transfer to look at this problem of instability. I'll talk about some of our more recent work on incorporating physics by using physics-informed architectures and physics-informed loss functions, particularly to deal with the small data regime. So we are building symmetries, some of the conservation laws into the neural network. And as you will see, it helps in the small data regime. And even though I don't think I will have time, but I'll very briefly mention some work that we are doing on using transfer learning to enable neural networks to do extrapolation. So the system that we are using is two-dimensional turbulence. The governing equations are simply this equation for vorticity, omega, and the stream function psi. This is the Jacobian, the nonlinear term. This is the Reynolds number. This can be a forcing on the system. For now, we assume that there is no forcing. And here I'm showing you an example of a direct numerical simulation, which basically at a given Reynolds number, like 32,000, if you have enough resolution, for example, around 2,000 Fourier modes in each direction, we can solve these equations without any further approximation. And here we have started with a specific initial condition that had a specific energy spectrum. And then we let the system run. And at some point it comes to self-similar regime. And that's where we do our training and testing. So now let's say we can't do DNS, it's too expensive, and we want to look at basically what's called large-eddy simulation. When we take these equations and we filter them. So here over bars, basically it means a filter and coarse graining. We can just use a simple Gaussian filter or a box filter, anything like that. And we know that, again, Tim already talked about this, we can almost write our equations in terms of the result value, the filtered variables, but we'll see that there would be a residual term that looks like this. And I'm going to call this term pi, which is basically the divergence of the stress tensor. This is where the effect of the turbulent eddies are, and this is the SGS term. So obviously there is an advantage in looking at LES compared to DNS in terms of computational power that you need. We can easily, for example, at this Reynolds number, reduce the resolution by a factor of 8 in each direction. We can take larger time steps. So already a factor of 640 fewer degrees of freedom that we can use in LES simulations. But then the challenge is how to represent pi only in terms of the result variable. So we can close these equations. Again, it's the usual problem. And there has been a lot of work on this. Maybe one of the best known work actually developed for weather forecasting was by Smokorinsky, where you can, for example, assume that pi is just diffusive, so that basically the turbulent eddies are just going to do diffusion. So you can basically use eddy viscosity times the Laplacian of omega, and this is going to be the parameterization. So what we are trying to do now is to basically leave that to a neural network to learn this relationship between pi and the result variables from DNS data, and then we couple it with this LES solver and see what happens. And most of what I'm going to talk about is already in this page. It is available on arXiv. So again, there has been a lot of work on physics-based models, but one major problem with physics-based models is that many of them only account for diffusion, and they do not account for what's called backscattering, or that you can think of it as like anti-diffusion. Just to demonstrate this issue, let's define a subgrid-scale transfer function T that I define as pi times Laplacian of omega bar. Notice that for models like Smokorinsky, or here I'm looking at a more basically modern version of it called dynamic Smokorinsky, if eddy viscosity is positive, which is what's used in practice, T is always going to be positive, which basically means that, again, the eddies only do diffusion. So, but let's see if that's always true or not. So here is an example of the filtered vorticity field from the DNS simulation. So the box here in the second row, you kind of see this zoomed in. This is what the filtered DNS gives us. So this is, you can treat this as the truth. And you see that a lot of grid points, they are red, if you zoom in as well. So this is the forward cascade. This is the grid points when we have diffusion due to the smaller scales. But also you see that there are a number of grid points, and not small, there's a good number of them, that it's blue. And this is where you have backscattering. This is when the unresolved scale, where the smallest scales is actually forcing the resolved scale. And again, you can think of it as anti-diffusion. This is something that is known that in modeling of the atmosphere, in modeling of ocean, modeling of a lot of the fluids, is actually something that physically exists and is important. But many physics-based models do not account for it because it can lead to instabilities. For example, the Smagorensky model, as you see here, it's all red. It only does diffusion, which is very good to stabilize a numerical solver, but again, it doesn't take care of all the physics. So what we want to do is that, particularly we want to see whether spatially non-local, non-parametric DDP, for example, using convolutional neural networks, can do this basically better, can account for both diffusion and backscattering and correctly. I'm not going to go through the details of the CNN that we are using, but it basically has 10 layers, 10 convolutional layers. The input is the filtered stream function and vorticity, and the output are those pi terms. For now, we start by using a simple loss function and basically MSE that is shown here. I emphasize that for now, the architecture of this neural network and the loss function, they are both physics agnostic. There are also other things like it's deterministic, it doesn't account for memory, but those things can be added to it later. But let's see what we can do with this physics agnostic CNN. So first we look at what's called a priori or offline test. So here, this is, again, the truth from filtered DNS. This is what our CNN does on the same sample. You see, if you look at the whole domain, or if you can let this zoomed in part, it does a great job in capturing all these scales, whether they are doing backscattering or forward transfer. This is also another neural network. This is just a MLP feed-forward network from another paper that had been already published in JFM. And you see that this one is local. So it does basically look at every grid point. This one also does a pretty good job if you look at the smallest scales, capturing both backscattering and diffusion. And then these are just for specific samples. We can look at the average of pattern correlation between the true pi terms and the predictions from the machine learning method. And the physics-based model will see that the machine learning methods have much higher pattern correlations averaged over hundreds of samples compared to these physics-based ones. But we know that this is not the whole story. For example, in this paper, what they found was that if they couple this ANN with their basically coarse-resolution solver, it blows up. So what they did, it has been done in many studies, is to take this and wherever it does anti-diffusion to kill that. And so the model becomes diffusive, it becomes stable. But again, you lose some of the advantage of what you were hoping to get from a data-driven approach. So in our work, we wanted to see whether with our CNN, we can get a stable, basically parameterization without doing anything. And one thing we did, we started looking at how this depends on the number of training samples. So N here, this is the number of training samples. We look at the training samples from 500 to 50,000, and we look at that pattern correlation. We'll see that even with 500,000, we have a pattern correlation of 0.78. And basically with 100 times more data, it gets to 0.93. But also here in the last row, I show you basically the fate of a simulation, a coupled simulation. We couple this CNN with the coarse-resolution solver. And we'll see that even for a case when this pattern correlation is 0.9, we get instability. And only when we get to around 0.92 that we get a stable data-driven parameterization. So then what we did, and maybe this is the first kind of knowledge guided thing that we did, is that we look at this C separately based on the grid points that do diffusion versus backscattering. And we found something that I think is sort of interesting and can be informative, and that is the diffusion, even with a small number sample, has been already learned well. You start with a pattern correlation of around 0.84 with 500 samples. And with 100 times more data, you increase this correlation by basically around 0.12. On the other hand, for backscattering, with a small training set, you start at around 0.5. But then, as you increase the number of samples, you get to around 90. And so it seems that backscattering, these are the two conclusions we drew from this, is backscattering is harder to learn data when the training set is small. And also we speculate that this disproportionately low accuracy for backscattering is the reason for instabilities. And again, this is for this system, but backscattering had been known even for physics-based systems to cause probably something like to capture, but then because it is forcing the system, if it's not captured accurately, it basically can cause instabilities. So after that, once we realized how to build basically a stable data-driven parameterization method, we found that when we couple this and look at the online mode, there's also actually pretty good. These are like basically comparison of the filtered DNS, which again, you can look at it as considered the truth with what the CNN does. The patterns look pretty good, much better than like the physics-based models that are very diffusive. You get better results in terms of short-term forecasting. And also you can look at the statistics, you see a clear advantage. For example, here I'm showing you the turbulence spectrum. Here, the solid blue line, that's the CNN, and it matches better than any of the other methods with the filtered DNS. And maybe the PDF of vorticity, looking at this tail, that's the best place to see the advantage of using a CNN. That is the solid blue line, it matches pretty well with the tails of the vorticity of the PDF with the FDNS, with the filtered DNS. On the other hand, these other methods, they're all pretty diffusive. So they might capture the bulk of the PDF rather okay, but they miss these extreme events. So this is what we have done so far, again, with the physics agnostic neural network. More recently, we have been looking at basically a force system. When we add a forcing at different wave numbers, and also we add linear damping. And so here we can basically generate, at the given Reynolds number, we can generate different kind of flows when they have forward cascade versus inverse cascade. They can have different scales when we do the simulation. So providing basically different test cases to look at what we do. And again, for all of these, we can build a stable, accurate LES for a range of parameters with 500 samples. Now, you might notice that 500 samples, this is much lower than that 50,000 sample. One thing I want to say is that it's just the same data, except that here we have basically we release the interval of sampling. So there's one thing that many people ask, well, how much data do you need to train a neural network, for example, for subgrid-scale modeling? And I think the answer is not just a single number in terms of the number of training samples, but the correlation, the inter-sample correlation also matters a lot. So here again, it's the same length of data, but with the basically increase the sampling rate, we still can get accurate results. But what we wanted to do next was to see if we build physics into the neural network, whether we can decrease that number from 500. And so we started looking at what the physics agnostic CNN might be missing. And get rid of this. So, and there are at least two things we came up with. One was, okay, anyway, so one of the things, like we started by doing a simple experiment, which is we generated a dipole that is shown here. Now, dipole would just move around, and we can calculate the filtered DNS of this and train a CNN, and the CNN would work pretty well. But let's say that we look at the sample that is this 90-degree rotated. Now, probably you and I look at this and say that, okay, the pi term should also be rotated by 90 degrees. We know some of the properties of the subgrid-scale term. On the other hand, now if you put this into the CNN, the physics agnostic CNN, it would produce this. And then you realize what the CNN is doing. The CNN looks at this and see that it came here. And what it does, it basically takes this or this and puts it on this side. And because this went here, it takes this part and put it here. So the CNN basically does translation but doesn't understand that this is a simple rotation. So of course, if you have a lot of data, if you have seen this and this, whichever you see later in the testing, it would work well. But it's a problem if you do not have a lot of data, if you are in the small data regime. Another problem with the physics agnostic CNN is dealing with some of the conservation laws. For example, you can show that because the nonlinear term only redistributes entropy, but doesn't basically produce it, or it's not a sink of entropy, that basically a domain average variable like this should be conserved. So you can think of, well, I like whatever comes out of my CNN to have the same domain average omega bar times pi with the FDNS. Now, we can look at this error, the error of basically this, when you have 50 samples, training samples versus 2000. And you see that here the error is 17%, here the 10%. The 7% difference might seem small, but actually it basically makes a difference in the terms of the stability in the online testing. I'm not showing those results, but this one blows up and this one is stable. So we came up with 3 remedies for this. So in the next couple of minutes, I'll try to quickly go through this. One is data augmentation, which is if you know some of the symmetries in your data, for example, you can take this and rotate it by 90 degrees, 180, 270, and have all these as the inputs to your data. And it's called data calculation that's been used in many studies in the past. Or you can just use something like an equivariant CNN, but some of the symmetries or really equivariances are built into the neural network. The difference between this approach and this one is here, I have the same filters, I'm rotating the inputs, but what something like a group CNN does, it takes the same input and rotates the filters. And finally, as you can guess, you can just build this entropy constraint as a self-constraint into the loss function. And we have done this, and these are some of the offline results. I'm not going to go through the details. One takeaway from this is if you have a lot of data, which are here, if you have 2,000 samples, adding physics doesn't help a lot. But if you do not have a lot of data, for example, if you have 50 samples, then you will see that these spaces that have some sort of physics baked into them do much better. And again, it's just a matter of 0.1, 0.2 in correlation, but that has a huge impact on the online performance. So here you get a big gain by adding physics in the small data regime. I'm not going to show the online results because of time, but you will see this effect of building physics in the small data regime into the accuracy. We also had done this building physics into the neural network in terms of symmetries. In the past, we have a paper that is in GMD about using data assimilation and using a transformer. And you can see, again, advantages there in terms of better capturing wave breaking and things like that. But again, I'm not going to talk about. I'll mention that we have a lot of success with using, okay, so I'm moving too fast. It's the last point I want to make. Using transfer learning, we have a bunch of papers on showing that for a chaotic system, if you increase the chaoticity or if you increase the Reynolds number, you can basically close the generalization gap and do some sort of extrapolation, even by a factor of 100 in the Reynolds number. So for the interest of time, I stop here. I should say that there's a paper that I've contributed to, but it's really led by Kartik Kashinats on physics for machine learning for weather climate modeling that has 10 examples of doing different things of building physics into the neural network that you might want to check out. So with that, I stop here. I'll just leave it here, and I'm looking forward to questions.
Thank you, Pedram. So I don't see any questions. I will note we have 2 minutes left just because we started a tiny bit late for you. So if anybody has questions, put them in Slido. I have lots of questions, but I will restrict myself to one. So actually, this is a bit more general. Stepping back, at near the end, you showed a plot showing how for small sample sizes, adding the physics in helped it a lot. But if you have a lot of data, you know, what do you need? It'll learn the physics, or what do you need physics for? My question is, from like a domain science perspective, is there anything to be learned by looking at what it was about the constraints that allowed those smaller sample sizes to still do as well? Does that make sense? To actually go in and try and understand why incorporating the physics when you did at those smaller sample sizes helped it learn faster? Does that make sense?
Yeah, I think there would be a lot of, if I understand your question, if your question is to then kind of dissect the neural network and see what changes was made, then sure, I think there can be a lot of value there to know how to better enforce those. Again, currently we are trying to see what has been done in machine learning in terms of equivariant neural networks or things like that, and none of them were designed for example, looking at Rossby wave breaking and better capturing that. But I think something that better guide us, I think that can be very, very helpful. Maybe something related to that, what we are doing is we are trying to understand what happens in transfer learning. Because in transfer learning, you only retrain 1 or 2 layers out of 10 or more. And actually, we have some results about this that we are working on writing up, that you can see some understanding of how the weights, for example, change. And I think if we can do that without the needing of actually some data from a more complicated system, that can be extremely useful. So, and maybe some of the methods that you have been working on, I think can be useful for this kind of understanding.
Great, thank you so much. And look at that, we're perfectly on our time here. So thank you so much, Pedram, for finishing our whirlwind of a day. And thank you everybody for joining us for day 1 of our second workshop on knowledge guided machine learning.